Dear colleagues, students, and ISC participants, I'm happy to make this presentation in this digital version of the International Astronautical Congress. The paper and the presentation I'm making is called Utilization of Gaseous Core Supercritical Nuclear Reactors for Space Power and Space Propulsion for Deep Space Missions. As you're aware, one of the important things to accomplish for a deep space mission is to be able to travel as fast as possible without being dependent on gravity assist systems for propulsion, and to have sustainable power for the spacecraft for the duration of the mission, and sustainable propulsion with high specific impulse for the duration of the mission. This is why gas core reactors is an important advantage. Basically, it's a type of a nuclear reactor, but instead of using solid fuel rods, it uses gaseous fuel in the form of uranium hexafluoride, which gives it a lot of advantages that we will discuss in this presentation. So, what is a gaseous core nuclear reactor? Just as I said a couple of seconds ago, it uses gaseous nuclear fuel uranium hexafluoride as the nuclear fuel. It's injected into the chamber for the nuclear reaction in gaseous form. There's actually nothing solid, no solid fuel rods, no solid scram rods, none of the typical nuclear equipment found in a typical nuclear reactor core, which gives it a lot of advantage, as you will see in a few minutes, in terms of deep space missions. It's a supercritical reactor. That means the criticality factor is slightly above 1, but the most important thing is temperatures as high as 10,000 Kelvin can be reached with a gaseous core nuclear reactor. Now you may ask, what is the advantage of having such high temperature? Well, we can understand from this slide. This is why high temperatures are very important for space missions. Equation on the left, you see specific impulse, ISP, which says exhaust velocity is divided by G, which is gravitational constant. And the equation on the right, you see UE, which is exhaust velocity again, which is equivalent to VE. You see an equation with various coefficients, but the important thing is the parameter just in the middle, which says TC, which is the combustion chamber temperature. Basically, if you look at that equation, it's a very basic algebraic equation, but it's very important in terms of rocket propulsion. Higher the combustion chamber temperature means you reach higher exhaust velocities, you reach higher specific impulses. So higher the temperature, higher the speed of the spacecraft. So this is a basic premise which allows us to travel farther and further if we have higher temperatures in the combustion chamber. That's why we use nuclear propulsion as a ways to get these high temperatures. But even with a typical fission reaction that you would get with a typical nuclear reactor, you'd reach around 1000 K, 1500 K, which is not so much higher than chemical rockets, but still it won't be enough to really give you that kick that you need for deep space missions or missions even beyond the heliopause. As you can see, it's very important to have high temperatures, and you saw from the previous slide, in fact I'll go back there just now so that you can see it, temperatures as high as 10,000 K can be reached in gaseous core reactors. So as you can see, if you input that 10,000 K here, obviously you would get higher exhaust velocity and higher specific impulse. That means you're able to go faster and further with your spacecraft without having to really worry about gravity assist. So what is a typical gas core nuclear reactor for propulsion? As you can see in the slide, in the middle you have the gaseous fuel which is being injected inside the gaseous core, and you also inject propellant, which is basically, for example, diatomic hydrogen. So as the nuclear reaction happens, the diatomic hydrogen gets heated up, and then you discharge it from the behind of the rocket. You can see in the typical shape, the nozzle, and the exhaust of this hydrogen, which is actually the fuel, not the nuclear fuel but the rocket fuel, would give you forward momentum for the spacecraft. So basically, in a typical gas core reactor, which can be used for spacecraft, would have a core length of 7 meters and roughly a diameter of 3 meters. So this is typically the size of a large communications satellite. So obviously this would be the core. Then you would have to have certain shielding in place, And after that shielding, if it's a manned space mission, you can obviously have the crew quarters up front with the shielding to protect them from the radiation. Or if it's an unmanned mission, it's much better. You would only need minimal shielding to protect the electronics equipment inside the spacecraft. And obviously you can go to various distances at very, very fast times. So for example, typically a Mars mission is about 600 days plus. So with a gas core nuclear reactor, you can easily go less than 3 months, about 90 days. That's without spending too much fuel and without using its maximum speed. So if you have a mission to heliopause, then you could use the maximum speed, maximum criticality, be there in a couple of months rather than decades it will take you to reach the heliopause. So this is just some examples to give you the idea of the benefit of a gaseous core nuclear propulsion over classical chemical propulsion or over classical nuclear propulsion. So going forward is a mission case study I have prepared for Barnard star. Barnard star, as you're aware, is about 6 light years away from our solar system, so roughly 5.96 to be exact. So if we have a spacecraft which can go at the speed of 0.4 c, which is semi-relativistic speeds, which is reachable by using a gaseous core nuclear reactor at high acceleration, a typical mission time would be close to 16 years. So it may not be possible for a manned mission, but for unmanned mission, I think a 16-year probe to reach Barnard star could be quite interesting. So using these type of nuclear reactors can give us the advantage using 21st century technology to travel to the outer edges of the solar system, to beyond, to other stars as well. If you're interested, this is my area of work. Please go to my website, www.drgavan.com, or you could go to my other website, www.aerospacelectures.com. Feel free to contact me. My area of expertise is nuclear space propulsion. I'll be happy to correspond with you. I wish you the remaining of the IAC to be successful as well. Thank you.